All right, let's go.
Number 10. The sun is at its most dangerous point in over a decade, and we are not prepared. Every 11 years, the sun goes through a cycle, a rhythm of rising and falling activity, driven by the churning of its internal magnetic field. At the quiet end of the cycle, solar minimum, the sun is relatively calm. At the peak, solar maximum, sunspots multiply, solar flares intensify, coronal mass ejections become more frequent and more powerful. The sun becomes a different machine. We are in solar maximum right now. In October 2024, NASA and NOAA jointly confirmed it. Solar cycle 25 peaked, and it has been more active, more violent, and more unpredictable than scientists initially forecast. When solar cycle 25 began in December 2019, the prediction was modest, a week maximum, comparable to the quiet cycle 24 that peaked between 2011 and 2014. The prediction was wrong from the beginning. By January 2023, observed sunspot numbers had exceeded forecasts for 27 consecutive months, not a small overshoot. In January 2023 alone, 143 X-class solar flares, the most powerful category the sun produces, had exceeded any other year on record since modern tracking began in 1996. X-class solar flares are not routine events. They are explosions of electromagnetic radiation so intense they can ionize Earth's upper atmosphere within minutes of their emission, disrupting radio communications on the day side of the planet at the exact moment the flare fires, not hours later, minutes. The radio blackout arrives at the speed of light before anyone has time to prepare. The October 3, 2024 X9 flare, the most powerful recorded since 2017, is the kind of event that forces aviation rerouting. Pilots flying polar routes are pulled off course to avoid communication blackouts and radiation spikes. High-frequency radio used for aviation, maritime navigation, emergency services, and military communication gets stripped, not gradually, instantly. Solar maximum is not over. The sun remains in elevated activity as of June 2026. The next solar minimum is not expected until approximately 2029 to 2030. Every week between now and then is a week in which the sun is capable of producing something far worse than anything it has done so far in this cycle, and most of our infrastructure is not designed to handle it. Number 9. The Gannon storm was a dress rehearsal, and we barely passed. On May 10, 2024, a sunspot region designated AR3664, stretching 17 times the diameter of Earth across the solar surface, erupted. Not once. At least 8 separate coronal mass ejections launched toward Earth between May 8th and 11th. Several were halo CMEs, ejections directed so precisely toward Earth that they appear in solar telescope images as a ring around the sun, a bullseye formation. Those CMEs stacked. They traveled through space at millions of kilometers per hour and arrived at Earth in a rapid succession of impacts. The combination produced the first G5 geomagnetic storm, the highest level on NOAA's 5-point scale since the Halloween solar storms of 2003. The most powerful storm to hit Earth in over 20 years. Auroras appeared as far south as Mexico, Puerto Rico, Portugal, Spain, Florida. Farmers in the American Midwest planting corn in the middle of the critical spring season found their GPS-guided tractors veering off course. John Deere dealerships texted customers to shut their GPS systems down. The disruption threw off position readings by up to 230 feet, well beyond the 3-foot accuracy precision farming requires. When the study was completed in 2025, the estimate was that American farmers alone lost over $500 million from that single storm. Aircraft lost vertical guidance at roughly 2,000 airports in the continental United States and Alaska. The system that helps planes descend within 200 feet of a runway simply stopped working. Airlines rerouted flights. NASA told the 7 astronauts aboard the International Space Station to move to the most shielded sections of the station and avoid the airlocks. One small satellite operated by a UK company called SEN was powered down for 4 days to protect its electronics. SpaceX's Starlink fleet experienced degraded service across its entire network. ESA's GOES-16, the primary geostationary weather satellite covering the Americas, stopped transmitting all data for nearly 2 hours on May 13th. The storm compressed Earth's plasmasphere, the donut-shaped reservoir of charged particles that co-rotates with our magnetic field, from its normal outer boundary of around 44,000 kilometers above Earth down to just 9,600 kilometers in 9 hours. A structure that normally changes gradually contracted to less than a quarter of its typical size in the time it takes to drive across a country. NASA had been running a tabletop exercise that same day, a simulation of exactly this kind of event, a training drill for emergency response to a major geomagnetic storm. When the Gannon storm hit, the representatives from 30 agencies were literally in the room running the simulation when the real thing started happening outside. The storm caused no catastrophic damage. Power grids held, satellites survived. The grid operators, aviation authorities, and space weather agencies had just enough warning to take precautions. But every analysis published since has reached the same conclusion. It was a preview, and the world was lucky. Had the storm been 20 to 30% stronger, had the CMEs arrived at slightly different angles or velocities, the outcome would have been different. Number 8. In 2012, a Carrington-level storm missed Earth by 9 days. The Carrington event, September 1st through 2nd, 1859. A solar flare so intense it was visible to the naked eye, astronomers Richard Carrington and Richard Hodgson independently watched it from Earth's surface at midday. The resulting CME traveled to Earth in 17.6 hours, a journey that typical CMEs take several days to complete, meaning this one was moving at an almost incomprehensible speed. When it hit, telegraph lines across North America and Europe sparked. Some shocked their operators, some caught fire at the terminals. Some telegraph systems continued transmitting messages after being completely disconnected from their power sources, running purely on the induced geomagnetic current from the storm itself. Auroras appeared in the tropics, in Cuba, in Colombia, at the magnetic equator. In 1859, the most advanced electrical technology on the planet was the telegraph network. It fried it. It recovered. Now imagine that storm hitting today. Lloyd's of London and the Atmospheric and Environmental Research Agency calculated the estimate in 2013. A Carrington-level event hitting the modern United States electrical grid alone would cause between $600 billion and $2.6 trillion in damage. In 2024 dollars, because the 2013 estimate has been updated since, the number sits between $794 billion and $3.4 trillion for the United States alone, not counting Europe, Asia, the rest of the world, satellite systems, undersea internet cables, military infrastructure, banking networks, or supply chains. Large high-voltage transformers, the kind that sit at the backbone of every national power grid, are not mass-produced items. They are custom manufactured. They weigh between 100 and 400 tons. A single replacement takes 12 to 18 months to build and ship. A Carrington-level storm would damage dozens of them simultaneously, maybe hundreds. The areas worst affected could be without stable power, not for days or weeks, for months, potentially for more than a year in some regions. In July 2012, a Carrington-class solar storm erupted from the sun, a full superstorm, the same scale as the 1859 event. It launched a CME at a speed of approximately 2,000 kilometers per second, nearly the same as the 1859 CME. It missed Earth by 9 days. 9 days earlier in its orbit, Earth would have been in the direct path of impact. On July 23, 2012, Earth was not in the right position. A week and a half of orbital geometry saved modern civilization from the most significant technological catastrophe in human history. The storm passed through the L1 Lagrange point, the position between Earth and the Sun where solar monitoring spacecraft sit, and was measured in full. It was real. It was massive. It did nothing because Earth happened to be somewhere else. The lead researcher on the study analyzing the 2012 event, Daniel Baker of the University of Colorado, stated directly that if it had hit, we would still be picking up the pieces. We have not updated the power grids. The transformers are not significantly better protected. The UK's Science and Technology Facilities Council released a comprehensive worst-case space weather report in January 2026, covering exactly this scenario. 80 pages, covering every system that fails, GPS unusable across entire continents, radio communications gone for days, airlines grounded, ships navigating blind, and a 100 to 200-year return period for events at this scale, meaning statistically one is overdue. Number 7. The sun's corona is 200 times hotter than its surface, and nobody knows why. The surface of the sun, the photosphere, has a temperature of approximately 5,778 Kelvin, hot enough to vaporize any material humans have ever worked with. The corona, the sun's outer atmosphere, the wispy halo visible during a solar eclipse, is 1 to 3 million Kelvin, between 200 and 500 times hotter than the surface below it. This violates the most basic principle of thermodynamics. Heat flows from hot to cold. It does not flow from cold to hotter. If you stand next to a fire, you get warmer as you move closer. You do not get colder near the fire and then dramatically hotter as you walk away from it. The corona should be cooler than the surface, not 200 times hotter. This is called the coronal heating problem. It has been known since 1939, almost 80 years. The most studied star in the universe, with more observational data than any other object in space by orders of magnitude, and one of its most basic physical properties, why its atmosphere is hundreds of times hotter than its own surface, remains unsolved. NASA built the Parker Solar Probe specifically to go inside the corona and find the heat source. It launched in 2018. On December 24, 2024, Parker completed its closest ever approach to the sun, 6.1 million kilometers from the solar surface, traveling at 690,000 kilometers per hour, the fastest object ever built, 0.064% the speed of light. What Parker found when it first entered the solar wind near the sun were hundreds of S-shaped magnetic field reversals, kinks in the magnetic field that briefly flip its direction before snapping back. Scientists named them switchbacks. These structures contained huge amounts of stored magnetic energy. The hypothesis was that as switchbacks propagated through the corona, that energy released into the surrounding plasma and heated it. Then, the University of Michigan team analyzed 14 complete orbits worth of Parker data and found something that shut down the most popular explanation. Switchbacks are abundant in the solar wind. Inside the corona itself, where the heating actually needs to happen, they are absent completely. If switchbacks were generating their energy at the solar surface and driving directly into the corona to heat it, they would be most concentrated inside the corona. They are not there at all. The cause of switchbacks is itself still debated. One camp argues they originate from colliding magnetic field lines at the sun's surface, collisions that vibrate like plucked guitar strings and send waves into space. Another argues turbulence in the solar wind itself produces the S-shaped bends after they leave the sun. Both camps remain active. Neither has been ruled out. What Parker has established is this. Whatever is heating the corona is not what scientists expected. The leading mechanism was tested by putting an instrument directly inside the region in question. The data did not support it. The actual heating process in the outer atmosphere of a star 8 light minutes from Earth remains unknown. Number 6. The sun is stripping Mars bare, and once did the same to Earth. Mars today is a frozen desert with an atmosphere 100 times thinner than Earth's. Average surface temperature of minus 60 degrees Celsius, no liquid water on the surface, no magnetic fields protecting it. 4 billion years ago, Mars had a thick atmosphere. Liquid water flowed across its surface. River valleys stretch across the ancient southern highlands. Delta deposits, rounded pebbles and Gale crater worn smooth by flowing rivers. The evidence of a wet, warm world is embedded in the geology. Then it lost its magnetic field, and the sun took the rest. Without a global magnetic field, the solar wind, the continuous stream of charged particles flowing outward from the sun at 400 to 800 kilometers per second, hits the Martian upper atmosphere directly, No shield, no deflection. The solar wind strips ions from the top of the atmosphere and carries them into space, continuously, permanently. NASA's MAVEN mission, Mars Atmosphere and Volatile Evolution, measured this process directly from orbit. During solar events, the rate of atmospheric stripping spikes dramatically. When a solar flare or CME arrives at Mars, the erosion accelerates. The atmosphere bleeds faster. MAVEN calculated that the sun strips roughly 100 grams of Martian atmosphere into space every second. During solar events, every few weeks, that rate multiplies. Over 4 billion years, the sun eroded the Martian atmosphere from thick enough to support liquid water in a greenhouse climate to the near vacuum that exists today. Earth survived because of one thing. Its liquid metallic core generates a global magnetic field through a planetary dynamo, the geodynamo. That field deflects the solar wind around the planet rather than letting it impinge directly on the upper atmosphere. The Van Allen belts trap charged particles. The magnetosphere stretches away from Earth on the night side in a long tail absorbing solar wind energy. If Earth's geodynamo ever fails, if the liquid outer core solidifies enough to stop generating the field, the solar wind begins doing to Earth what it did to Mars. On a geological timescale, the atmosphere would erode, oceans would evaporate, the surface would become uninhabitable. Earth's magnetic field is not static. It is weakened by approximately 10% over the last 150 years. It has reversed hundreds of times over geological history. During a reversal, the field does not switch instantly. It weakens dramatically, may become multipolar and fragmented before reforming with opposite polarity. The transition takes thousands of years. During that window, the protection is significantly reduced. The sun is not waiting. Number 5. The sun fires radiation at astronauts, and we launched 4 of them during solar maximum. In April 2026, NASA launched Artemis II. 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen, on a 10-day loop around the moon and back. They launched at solar maximum during the most active period of the most active solar cycle in a decade. The timing was deliberate. NASA and ESA have been studying how radiation affects humans in deep space for years. The data that comes back from Artemis II, including from radiation dosimeters worn by the crew, is essential for planning the longer Artemis III mission that will actually land people on the moon. But the risk was real. NASA's own documentation acknowledged astronauts could face nearly lethal doses of radiation from a sufficiently powerful solar particle event without adequate warning and shielding. The Orion capsule has shielded areas. Astronauts' monitoring systems could shelter in place during a flare or CME event. But solar particle events can intensify faster than warning systems can respond. During the 2003 Halloween solar storms, astronauts aboard the ISS were ordered to take their cautionary shelter in shielded sections of the station. A solar particle event that arrived without adequate warning during an EVA, a spacewalk, could expose an astronaut to a radiation dose associated with serious acute radiation syndrome. A large enough event could be fatal. The warning system from the sun's surface to Earth is approximately 8 minutes for photons and between 15 minutes and several days for the plasma of a CME, depending on speed. A fast CME leaves almost no margin for response. Parker Solar Probe and spacecraft at the L1 Lagrange point, like Discover, provide early warning, but that warning is measured in tens of minutes to a few hours, not enough to return from a spacewalk, not enough to abort a lunar surface excursion. Every future human mission beyond Earth's magnetosphere, to the moon, to Mars, to anywhere, will take place under a continuously firing charged particles and occasionally hurling billion-ton plasma clouds at everything in the inner solar system. Number 4. The sun is about to start its next cycle before the current one is even over. In July 2024, the Royal Astronomical Society published something that surprised solar physicists. Rumblings of solar cycle 26 have already been detected inside the sun. In acoustic oscillations, essentially sound waves moving through the solar interior, Scientists found the signature of early magnetic activity consistent with the very beginning of a new solar cycle, not at the surface, deep inside. The sun is not finished with cycle 25. We are in it right now. The current solar maximum has not yet concluded. The next solar minimum of cycle 25 is still years away, expected around 2029 to 2030, and the sun is already preparing the next one. This is not unprecedented. Each cycle overlaps with the beginning of the next at the deepest levels. But the early rumblings of cycle 26 detected in 2024 suggest the cycle overlap may be more active or earlier than typical. Scientists do not yet have enough data to characterize how strong cycle 26 will be. The prediction panels that got cycle 25 dramatically wrong, forecasting a weak maximum when they got one of the most active cycles in decades, are now exercising considerably more caution in their preliminary assessments. What is known is that the sun does not rest between cycles in the way the simplified 11-year model implies. The transition from one cycle to the next is not a flat, quiet period. Both cycles operate simultaneously in different hemispheres and different layers of the solar interior during the overlap. Activity during the transition is unpredictable. From 2026 onward, the sun will be simultaneously winding down cycle 25 and spinning up cycle 26. Two overlapping cycles, unpredictable interactions. Scientists watching for the precise moment of transition, called the terminator event, that marks the true flip between one cycle and the next. One cycle is not enough warning. The sun has already moved on to the next. Number 3. The sun's poles are more terrifying than we knew, and we just saw them for the first time. In June 2025, the European Space Agency announced something that had never happened before in the history of solar observation. For the first time, humanity was seeing the sun's poles from directly above and below. ESA's Solar Orbiter spacecraft, launched in 2020, had been gradually tilting its orbital plane using Venus gravity assists to reach higher and higher latitudes above the ecliptic. In June 2025, it reached an inclination sufficient to directly observe the solar polar regions at an angle never before achieved. Not from the side, from above. What Solar Orbiter revealed at the poles was more complex and more chaotic than any model had predicted. The polar regions are the birthplace of the fast solar wind, the stream of particles that flows outward at 500 to 800 kilometers per second, faster than the slow solar wind that originates from the sun's equatorial regions. Understanding where fast solar wind originates and how it accelerates has direct implications for predicting space weather events at Earth. The polar magnetic field is the driver of the entire solar cycle. The sun's cycle of increasing and decreasing activity is ultimately caused by the winding and unwinding of magnetic field lines as the solar equator rotates faster than the poles. The magnetic field generated at the poles during solar minimum seeds the activity of the next maximum. What Solar Orbiter found was that the polar magnetic structures, the corridors that feed the fast solar wind, are far more fine-grained, more dynamic, and more energetic than existing models described. Tiny, intense magnetic structures called campfires, miniature flares just a few hundred kilometers across, are continuously firing across the polar surface. Their relationship to the fast solar wind and to the coronal heating problem is being actively investigated. In June 2025, scientists were also seeing the sun's corona from above for the first time. What that perspective reveals about the global structure of the magnetic field, and therefore about where the next cycle's active regions will form and how intense the next solar maximum might become, is still being analyzed. The poles of the sun were dark to us for the entirety of human history. We saw them for the first time in 2025, and they are far more active than anyone expected. Number 2. A single solar flare can knock out every satellite in low Earth orbit simultaneously. There are currently over 10,000 active satellites in low Earth orbit. SpaceX's Starlink alone operates more than 7,000 of them. Add Amazon Kuiper, OneWeb, Chinese constellations, military satellites, weather satellites, GPS satellites, and scientific missions, and the number of operational spacecraft has increased by an order of magnitude in a decade. During the May 2024 Gannon storm, the expanded upper atmosphere, heated by the geomagnetic storm and puffing outward, increased drag on satellites orbiting in low Earth orbit. More atmospheric molecules at higher altitudes means more friction. Satellites slow down, their orbits decay faster, they fall. During the Gannon storm, ESA's ICESat-2 lost altitude and entered safe mode. NASA's Sirbe CubeSat deorbited prematurely, 5 months ahead of schedule, having been pushed out of its stable orbit by the enhanced drag from a single geomagnetic storm. Half of all low-orbit payloads simultaneously performed collision avoidance maneuvers, the largest coordinated satellite migration in recorded history. Over 10,000 spacecraft, all adjusting position at the same time. Each maneuver introduces position uncertainty. Position uncertainty increases collision risk. A study published in 2026 tracking what researchers called the crash clock, a metric measuring how quickly a cascade of collisions could begin following a severe solar storm that disrupted tracking and positioning, found the window had been shrinking dramatically. As of March 20, 2026, the metric stood at 3.0 days. In June 2025, it had been 5.5 days. In January 2018, it was 164 days. The window between the onset of a severe solar storm, which disrupts tracking and forces satellites into safe mode, and the first catastrophic collision is shrinking as the number of satellites grows. In June 2025, objects were passing within 1 kilometer of each other in low Earth orbit roughly every 36 seconds. Every 36 seconds. A sufficiently powerful geomagnetic storm, one that simultaneously enhances atmospheric drag, disrupts satellite tracking systems, forces thousands of satellites into safe mode, and eliminates real-time coordination for hours, could be the trigger event for a Kessler syndrome cascade, the chain reaction where debris from one collision creates debris that triggers the next, until low Earth orbit becomes permanently unusable. GPS would go silent. Internet satellite networks would go dark, weather prediction would go blind, military communications would fail. Every modern system that depends on space-based infrastructure, which in 2026 means essentially every modern system, would be affected simultaneously. Number 1. The sun's corona is already inside the solar system, touching every planet. This is the finding most people have never heard, and it changes the picture of the entire solar system. For the most of the history of solar physics, scientists assumed the sun's atmosphere ended at a specific boundary, the point where the outward pressure of the solar wind overcomes the sun's gravity and the corona transitions into the interstellar medium. This boundary is called the Alphen critical surface. Beyond it, according to the models, particles are no longer in the sun's atmosphere, they are in the solar wind. Parker's solar probe found that this boundary is not a smooth sphere. It is deeply irregular. It has spikes and valleys, wrinkles. During some of Parker's close passes, it was inside the Alphen critical surface, inside the sun's corona, then outside it, in the solar wind, then inside it again, multiple times on a single orbital pass. The boundary is not a fixed distance from the sun. It moves, it shifts, it fluctuates based on magnetic structures on the solar surface. The practical implication is strange and significant. The sun's corona, technically, extends outward in jagged, irregular structures across the inner solar system. When Parker flew through a structure called a pseudostreamer, a massive arc of magnetic field rising from the solar surface, conditions changed dramatically. The barrage of charged particles quieted. Switchbacks dropped to near zero. It was, one researcher described, like flying into the eye of a storm, a region of the corona quiet enough to be clearly distinguished from the chaotic solar wind surrounding it. But what this also means is that the corona's boundary is not where the textbooks say it is. The sun's atmosphere is not contained within a few solar radii. It extends outward in irregular structures whose full extent and implications for space weather prediction are still being mapped. This solar wind, which hits Earth continuously, shapes the magnetosphere, drives the aurora, strips the atmosphere of Mars, is not a separate entity that begins cleanly at some fixed distance from the Sun. It is the outer continuation of a corona whose exact shape is only now being understood after a spacecraft flew directly into it for the first time in history. The Sun reaches every planet in the solar system, and we are only beginning to understand how. 10 things scientists have found about the star you orbit, right now. Not theoretical futures, not distant astronomical abstractions, the most active solar cycle in over a decade happening above your head while you watch this. A storm in 2024 that compressed Earth's protective plasma shield to a quarter of its normal size and cost farmers $500 million in GPS losses. A Carrington-level event in 2012 that missed Earth by 9 days. 9 days that nobody is talking about. A corona 200 times hotter than the surface below it, with no accepted explanation after 90 years of trying. A sun stripping the atmosphere from planets that do not have magnetic fields to defend themselves. Astronauts launched into deep space during solar maximum because we need the radiation data, even though the radiation data we are collecting exists partly because the risk is real. A next solar cycle already stirring in the interior before this one is finished. Poles observed for the first time in human history in 2025, showing structures more complex and more energetic than any model predicted. Satellites falling faster every time a storm hits because there are too many of them and not enough space between them. And a corona whose boundary is not a clean sphere, but a jagged, shifting, irregular shape that extends deep into the solar system in ways our models are only now beginning to account for. The sun keeps you alive, and it is completely indifferent to whether it keeps doing that. Subscribe to Cosmic Hives. See you in the next one.